Lesson 3.8. We're going to start with the derivative of the natural log function, which is 1 over whatever you are taking the natural log of, that goes in the denominator, times the derivative of whatever you're taking the log of with respect to x. Because traditionally these will probably be some function of x, but you can change up the variables. Then what you have to recall is that this formula right here for the derivative could entertain negative values, but definitely not 0. Because it's coming from a logarithm, you have to remember you can only take the log of positive numbers, so there's a domain restriction on what you have in the derivative. So the regular logs, like the common logs, or log with any base other than e, what we do is 1 over the stuff you are taking the log of times the natural log of the base. So this is ln of a. And then by the chain rule, du dx at the end. For the absolute value around the quantity inside, the only changes that come into play is over here in that domain restriction, because negatives now inside can happen. When you have positives, it comes out straightforward. When you have a negative, by the chain rule, you're going to create another negative. That's why it comes out to be the same thing, whether it's positive or negative inside. So it's 1 over the stuff you're taking the log of without the absolute value times du dx, and note the restriction here. Putting them into practice, how does this work? I'm going to find dy dx, or y prime, of this function. Start off, it's 1 over the stuff inside the log, so we have that, times, by the chain rule, the derivative of this inside, or the derivative of the stuff, negative 2x. Simplifying, we have negative 2x over 9 minus x squared for the log's derivative. A handy-dandy shortcut way to think of it is 1 over d stuff times 1 over stuff times d stuff. 1 over stuff times d stuff. Y prime, I have a quadratic times a logarithm. Because I see a product and the log is part of the product, that means that the product rule dominates for this derivative. I'm going to keep x squared as is. Then I'm going to do the derivative of the logarithm. 1 over your stuff that you have inside. A little extra because my base is not e, so I'm going to say times the natural log of 4. And then by the chain rule, the du dx, this is like saying x to the negative 1. Negative 1x to the negative 2 is what I would have there for the derivative of the inside. Plus, if I flip it around, now I'll take the derivative of the quadratic, which is 2x, and I would keep the log the same. Being very careful with logarithms with parentheses for who you are taking the log of. This one simplifies down to, we have x squared times 1 times negative x to the negative 2. Well, these combine. I add my powers. Those x's are gone. I have negative 1 over the natural log of 4 being divided by x. Plus, nothing to be done here. That stays. This does clean up a little bit more because we do not want to have the derivative as a complex fraction. So dividing by one quantity is like multiplying by its reciprocal. I end up with negative x over the natural log of 4 plus 2x log base 4 of 1 over x. And this, I forgot to do my domain over here. My domain for this one is I have to be careful what's going to make it only positive. So to make it only positive, I want to stick to values that are within 3 and negative 3 to make that go to a 9. So I'm going to say negative 3 is less than x, which is less than 3 for this particular derivative. And for this derivative, we have to worry about, in this case, we can't have it be 0, and we can't have it be a negative quantity, so I'm going to say x is greater than 0. The next problem, y prime equals, I look at what I have. I have a quotient tucked inside of a square root, which is part of the logarithm. So you have a lot of chain rule stuff here because you have a quotient, you have a square root, and then you have the logarithm. You can do a rewrite to this and think of it as the natural log of 4 plus x squared over 4 minus x squared, all raised to the 1/2. The reason I'm doing this is I'm thinking before I'm jumping in to make the derivative the easiest possible version. That 1/2 power, because of logarithm properties, moves. So now instead of dealing with a 1/2 power inside as the middle piece, it now is just a coefficient. So looking before you jump in can save you time and energy on the algebraic part of doing the derivative. So that 1/2 now, constant multiplier. Its derivative is going to be 1/2 times, and then I'm going to work on the derivative of the natural log, which has the natural log component and the quotient component. So that power rule is now gone because it became a constant in front. Natural log derivative is 1 over the stuff that you have. So I have 4 plus x squared over 4 minus x squared times the derivative of the inside, which is a quotient rule. And actually, now that I'm thinking about it, we could go even further, and instead of doing the quotient rule, watch this. Natural log of the quantity 4 plus x squared minus natural log of 4 minus x squared with a 1/2 in front. That will make it even easier algebraically. So let's switch and do that instead. You could easily do it this way and get the same answer, but again, looking before we leap is always good. So I'm going to start with the first piece, which is a composition, just not as crazy as the composition I was about to do. So I'm going to say 1/2, and then I'm going to change it to this now instead of times because I note I have subtraction. Derivative for a logarithm is 1 over what I have times the derivative of the inside. Instead of writing them all out over here, you can always go back and just throw them into your numerator right away. That'll save you some writing and some cleanup later on. So it's 1 over what we have times the derivative of the inside minus, again, it's a logarithm, so I have 1 over what I have times the derivative, and again, you can do it here, times the derivative of the inside, or swap out your 1 and say times the derivative of the inside, which is a negative 2x. Then, the only simplification here is we have 2 negatives, that becomes a positive. And this is a much easier algebraic workout than if you had started with that original expression and done chain rule for 3 different pieces. So be on the lookout for those types of maneuvers. Up at the top here now, we have the limit as h goes to 0. Hopefully by now that's becoming very, very familiar to you. If I see a limit with h approaching 0, I am recognizing this is my definition of the derivative. So it's f of x plus h, or a plus h, minus f at x all over h. Well, that's its format. So the f of x, the function, has already been evaluated in this piece. So it's the value for the function at a certain input. So now I'm going to trace back over here and say, okay, what is that function and what is its input? I'm looking for the a plus h or the x plus h, which is right here. So I'm evaluating the logarithm at 100. Well, what is my function? There it is on the outside. F of x is equal to the log, common log of x. If I take a look at 100, just to confirm that this is indeed what we're supposed to have, what is the log of 100? Well, the log of 100 is 2. So there's my f of x at the given input. What these all represent would be the derivatives, because this is the derivative setup. So I'm going to now take the derivative using the log properties we just learned. 1 over stuff inside the log times the natural log of its base. By the chain rule, the derivative of x is 1. What we're finding next is the derivative at 100. So we have 1 over 100 times the natural log of 10, which is choice B. Tangent lines, we've been doing those for a while. You could pause the video and try it yourself before we do it together. I want to find first the y value, because I need a point and a slope. I'm going to start with g of 3. Making sure as we go through problems we label the different parts of what we're doing. 1 over what we're taking the log of, because it's a group, that is in parentheses, times the natural log of the base. Necessary to have your parenthesis here, otherwise it would assume the natural log of 5 is only multiplied by the 7. Then I go up to the top, and I say, okay, now I have to do the derivative of the inside. So the derivative of the inside would be 4w squared, because I'm working with w. Oops, I'm going through and doing derivative when I said I was going to evaluate. So we're just going to change this notation and say g prime of w. So we have 1 over the stuff we have, natural log of the base, times the derivative of the inside. So there's my g prime of w. See the importance of labeling so you know your pieces and you don't get distracted like that. All right, g prime at 3. 4 times, oops, another mistake. That's just 4w. 2w squared, 4w. So 4 times 3 is 12 divided by 3 squared is 9, times 2 is 18, plus 7 is 25, times the natural log of the 5. There's our slope. Now we'll do g of 3, and g of 3 is log base 5 of, when we plugged in the 3 here, we had 25 in the derivative, so it would be 25 in the regular function. And then 5 to what exponent becomes 25? That would be the number 2. So g of 3 is 2. The equation of your tangent line, y minus 2, equals 12 divided by 25 natural log of 5 times the quantity of x minus 3 for the equation of the tangent line. Last problem, you have m of x is equal to this particular function. We're going to find the value for b such that the derivative at pi over 4 is going to come out to be 8. Well, if we're talking about the derivative at any value, let's find the derivative in general. I would highly recommend doing the derivative in general before you start plugging in, because you can mess yourself up. Derivative is with respect to x, linear function, that piece goes to b. Plus, this is a composition with two pieces, derivative of the ln 1 over what we have inside the logarithm times the derivative of the inside, which would go to secant squared. Then what do we know? We know at pi over 4, the derivative is 8. So I'm going to say the derivative value is 8 anytime I see a pi over 4. Well, pi over 4 is your 45, 45, 90. And I want a secant value, then square it. Secant is flip of cosine. Cosine is adjacent over hypotenuse. So I have hypotenuse over adjacent, which is a root 2. And then I'm going to square it. The tangent out of 45, opposite over adjacent, is a 1. When we simplify this, we end up with 8 equaling b plus a 2. So the value for the b that causes that derivative to happen is 6.